Welcome. This presentation is based on the article Project of Innovative Open Multi-Domain Early Warning Platform EnviWise for Adverse Events in Water Bodies and Streams by Blaszczewski, Peckold, Krolikowski from Koszalin University of Technology, Grunt from Hilo Solutions Limited and Bielicki from EnviWise Limited in Poland. The project's goal is to create a novel, open platform for early warning of water quality issues, such as salinity, acidity, temperature, chlorophyll, etc. The platform uses autonomous buoys with customized sensors to measure different points in water bodies and streams. The platform provides remote and distributed water monitoring for various stakeholders, such as local authorities, water managers, and businesses affecting water resources. The Open Data System and the Universal Buoy technology will enable the collection of desired chemical and biological parameters, in accordance with the Water Framework Directive, using standard and reliable sensors. The buoy design will allow both wired and wireless data transmission from local measurement points to the buoy station. The platform will also use machine learning and data analysis to optimize the data acquisition with a minimal number of buoys. The sensor dispersion and the buoy station autonomy will ensure measurement flexibility and scalability. The presentation will proceed in the following order: introduction, overview of the project, motivation, objectives, challenges, system components and functionality, description of the measurement points, buoys, sensors, data acquisition, transmission and aggregation, machine learning and predictive algorithms, explanation of the prediction and classification algorithms, data pre-processing, feature extraction, model selection, water parameters to be monitoring, prediction algorithm, details of the algorithm, inputs, outputs, assumptions, limitations, classification algorithm, details of the algorithm, inputs, outputs, assumptions, limitations, conclusion, summary of the main results, contributions, implications, future work. A measuring buoy for water purity monitoring constitutes a vital device employed in gathering data pertinent to water quality in lakes, rivers, and various other aquatic bodies. Typically outfitted with an array of sensors, the buoy can assess multiple parameters, including water temperature, pH levels, dissolved oxygen, turbidity, and other water quality indicators. The information procured by the measuring buoy facilitates monitoring fluctuations in water quality over time and identifying potential pollution sources or environmental concerns that might adversely impact the aquatic ecosystem and proximate human populations. Measuring buoys serve as formidable instruments in comprehending and managing natural water resources, providing invaluable insights to environmental scientists, policymakers, and others dedicated to safeguarding, conserving, and administering our natural water resources. Continuing research and development in this domain will likely yield further enhancements in the technology and its applications. In recent years, rapid advancements have occurred in this field, with several key developments and improvements including the following aspects. Real-time monitoring represents one of the most notable benefits of measuring buoys, attributed to their capacity to collect real-time data on water quality. This enables prompt responses to environmental shifts and swift identification of pollution sources or other hazards. In this context, Geographic Information Systems, GIS, can be utilized to integrate data from measuring buoys with other environmental information, such as land use patterns and hydrological data. This aids in discerning patterns and correlations in the data, informing management decisions based on the location of threats. The introduction of multi-parameter sensors in measuring buoys, which can simultaneously measure various parameters like temperature, dissolved oxygen, pH levels, and turbidity, simplifies the process of gathering comprehensive data on water quality. These sensors are often designed to provide real-time data and are calibrated to ensure accurate measurements. The accuracy of sensors employed in measuring buoys may be influenced by factors such as fouling or biofouling, sensor drift, and sensor calibration. Addressing these concerns is essential to guarantee the accuracy and reliability of the collected data. Coupled with wireless connectivity, measuring buoys can transmit data wirelessly, facilitating remote monitoring and analysis. This feature proves particularly advantageous in extensive aquatic bodies where manual data collection from sensors may be hazardous or challenging. Data transmission can be executed using satellite, cellular, or other wireless technologies and ultimately relayed in real time to a central monitoring station. Data management is another critical issue to consider. Specialized software tools can be employed to store and analyze data collected by measuring buoys, allowing researchers and other stakeholders to identify trends, monitor water quality changes over time, and make informed decisions about resource management. Measuring buoys can generate substantial amounts of data, rendering the management and analysis of this data a complex task. Factors related to data quality, integration, and management can impact the utility of the collected data. Measuring buoys are most effective when utilized in collaboration with local communities and stakeholders. Fostering trust, sharing data, and developing management strategies with these groups can be challenging but are crucial to the long-term success of any water quality monitoring program. Data management is now significantly supported by machine learning and artificial intelligence. These algorithms can analyze data from measuring buoys to identify trends, anomalies, and other patterns that may be difficult to detect using traditional statistical methods, improving the accuracy of water quality predictions and informing decision-making. In conclusion, when evaluating monitoring buoys, it is essential to consider the technical challenges associated with their functionality. Specifically, power sources for these buoys typically comprise solar panels or other renewable energy sources to power the sensors and communication systems, thereby eliminating the need for frequent maintenance or battery replacement. Nevertheless, measuring buoys necessitate regular maintenance and servicing to ensure their operational efficacy and accuracy, which can be particularly challenging in remote or hard-to-reach locations. The costs of these units can vary. Although measuring buoys have become more affordable in recent years, they may still be expensive, particularly for small organizations or community groups, potentially limiting the accessibility of this technology for those who need it most. As evidenced by the above discussion, devices such as measuring buoys are integral to addressing the challenges posed by smart technologies and systems in today's world, including smart cities and smart transport. However, certain technological limitations exist. For instance, measuring buoys may be incapable of detecting specific pollutants, such as microplastics, and may prove ineffective in very shallow or rapidly flowing water. Consequently, the Envivise measuring buoy was designed to minimize some of these limitations while simultaneously fulfilling the aforementioned requirements. The technological challenges addressed during the project definition phase include 1. Design and implementation of a measuring station capable of real-time analysis of user-defined and individually tailored biological and physico-chemical parameters of rivers and reservoirs, such as pH, temperature, oxygen demand, oxygen saturation, salinity, conductivity, and water column height. For the current project and first deployment, sensors for conductivity, salinity, pH, temperature, and water column height will be utilized. The station must meet high operating standards in harsh conditions, IP68 according to IEC 529, maintain energy autonomy for at least 1 month, and provide reliable measurement data to the application server. The main technological challenge in this area is the appropriate design of the station and optimization of communication with the service server, as well as ensuring suitable energy autonomy too. Design and implementation of a central application, see Figure 1, for aggregation, analysis, presentation, and export of measurement data from monitoring stations, capable of also presenting data from the European Sentinel satellite mission. The application should enable real-time analysis of user-selected parameters from available sensors and map this data onto the presentation layer, as well as integrate this data with satellite measurements. The proposed platform will consist of, see Figure 2, autonomous measuring stations equipped with wired inputs and wireless communication modules, a central application with data integration and presentation services. The platform's planned functionalities include real-time monitoring of ecological and physico-chemical parameters of surface waters using distributed measuring stations and wired and wireless sensors, access to real-time measurement data through a web interface. Integration of measurements with satellite imagery, advanced trend analysis, historical event examination, and prediction of measured values, data preparation for further R&D activities. The monitoring buoy, see Figure 3, allows for the assessment of water quality and atmospheric conditions. It can be used in all types of water with temperatures ranging from 0 degrees Celsius to 50 degrees Celsius as a maintenance-free recorder for point tests, as well as profiling. Ideal applications include monitoring saltwater intrusion, surface waters, reservoirs, lakes, river mouths, spring water, beach areas, and stormwater runoff. In addition to sensors collecting atmospheric data such as solar radiation, pressure, temperature, air humidity, wind speed, and direction, the monitoring buoy also can evaluate water quality. The solution is characterized by 4 fundamental features: autonomy, fully autonomous operation without external power sources and wired communication modularity, ultra-compact design, reach, universal equipment, and interface configuration, as well as autonomous operation, allow for the creation of flexible measurement systems while maintaining all key properties of professional measuring stations. IoT, Internet of Things, compatibility with all leading IoT standards enables the selection of optimal wireless communication depending on customer needs and local system conditions. Data security. Data encryption in radio communication is based on the AES 256 standard, which means a 256-bit encryption key, practically unbreakable by today's computers. The presented measurement buoys are perfectly suited for monitoring weather conditions and water quality. The buoy is capable of wirelessly transmitting real-time measurement data and various data transmission standards to an aggregating server. Sensors connected to the measurement modules enable the creation of a distributed network of multiple measurement points, transmitting data via radio to measuring stations that directly send data to the Internet cloud without the need for cumbersome cable connections between individual sensors. The basic equipment of the buoy includes a hybrid buffer power system ensuring uninterrupted operation throughout the year, integrated monocrystalline PV panels 4x10W, a hermetic IP67 enclosure, an AGM battery with 12Ah capacity, full integration with the recipient's API. The measurement buoy has the following functionalities: automatic collection, archiving, and processing of measurement and visual data. The weather station ensures the storage of measurement data for a minimum of 30 days while maintaining the principle of overwriting the oldest data with new data. Transmission of collected data to the indicated system, indicating trends in changes and alerting of potentially hazardous weather conditions. Analyzing data to control measurement quality and generating alarms in case of adverse weather conditions. Supervision of the functioning of all sensors and devices. The station monitors the power supply and has the ability to perform technical diagnostics of measurement sensors. The autonomy and wireless operation of the measurement module are based on wireless communication standards. In accordance with the Internet of Things methodology, data aggregation obtained from measurement modules is sent to dedicated servers using GSM LTE technology, that is, Global System for Mobile Communications. This is the most popular mobile phone standard, offering voice and data transmission services worldwide. GSM directly refers to the 2G network standard, GPRS, EDGE, characterized by low data transfer speeds but high prevalence. The next network standard is 3G UMTS, HSPA, which is currently the most widely developed, and its coverage extends to most of Poland. The fourth generation cellular network 4G provides the fastest and best quality data transfer. Standards with the greatest potential in terms of energy efficiency and range are LTE-M and NB-IoT, Narrowband Internet of Things, standards. The solution supports the full spectrum of GSM LTE standards, focusing on NB-IoT technology. In the case of the availability of local infrastructure and wireless Wi-Fi networks within a compatible frequency, for example, 2.4 GHz, it is possible to minimize the operating costs of installation and communication with data servers based on this technology. Wireless radio networks Wi-Fi provide a range of up to 70 meters inside the building and up to 250 meters outside. Complementing the supported wireless communication standards is also an implemented module for receiving GPS Global Positioning System, Signal, a satellite navigation system, operating on carrier frequencies of 1575.42 MHz and 1227.6 MHz. Obtaining a signal from at least 4 satellites allows for accurate geolocation in 3-dimensional space and precisely synchronized time with an atomic clock. ensuring data acquisition occurs under strictly regulated conditions and with constant accuracy. The measurement, logging, and data transmission intervals can be adjusted to the customer's needs and set at the server's client panel. Measurement interval defines the frequency of receiving measurements from connected sensors. The value depends on the technical capabilities of individual sensors and the characteristics of physioclimate parameters. Logging interval defines the frequency of calculating received measurement data into minimum, average, and maximum values that have been aggregated in this period. Data transmission interval defines the frequency of sending recorded data to the server. The logging and data transmission intervals for measurement modules communicating via LoRa are the same. The software has been designed to make the best possible use of the architecture of the two cooperating processors. To achieve maximum performance and flexibility, a real-time operating system has been implemented. This system manages the execution of tasks depending on their priorities and allows for multitasking. Several tasks can be performed simultaneously. The main unit chosen is a processor with minimized energy consumption. It is intended for performing the necessary actions for the functioning of the entire system, management and supervision of the power supply system, and performing measurements with the highest frequency requirements, for example, atmospheric conditions measurements. The coprocessor, which is a unit with much greater capabilities and efficiency, serves as a subordinate system. Its task is to perform measurements at a lower priority frequency and communicate with the GSM module. After compiling a complete data packet, the coprocessor performs serialization and encryption. The prepared output information packet is then sent to the server via the GSM module. An essential parameter from a metrological point of view is the frequency of performing and reporting measurements. Due to the need to modify these parameters during system operation, the system has been programmed to automatically adapt them to the conditions or set them based on a specific customer command sent from the server. The software also provides the possibility of remote updates, OTA, over the air. The device periodically queries the server, and if a new software version is available, it downloads the update file. Then, at a convenient time, the processors are switched to bootloader mode, and the update is carried out. Thanks to this functionality, the device fully fits into the concept of the Internet of Things, allowing for fully remote management of the system and introducing any changes to the software without the need for hardware intervention. The data aggregated on the server in the database is presented on the control panel, see Figure 4, divided into sections of current measurement data and a summary of historical data in the form of visualization on the chart. Monitoring water parameters is an essential task for maintaining the health and safety of aquatic ecosystems. Water parameters include physical, chemical and biological factors that affect the quality of water and the organisms that live in it. Some of the most important water parameters are temperature, pH, dissolved oxygen, ammonia, nitrite, nitrate, phosphate, salinity and hardness. These parameters can be measured using various methods and instruments, such as test kits, probes, meters and sensors. Monitoring water parameters regularly can help detect any changes or problems in the water and take appropriate actions to correct them. Planned measurements of buoy sensors, vertical temperature distribution in the water column, TV. Temperature is one of the most important physical factors influencing the rate of reactions occurring in all ecosystems, including aquatic ones. Temperature also affects the value of other parameters, including electrical conductivity. The device automatically compensates the conductivity level to a value of 25 degrees Celsius. The vertical temperature distribution is measured by evenly distributing 5 dedicated semiconductors, digital integrated circuits placed in metal sleeves at levels of 0 cm, -100 cm, 200 cm, -300 cm, and -400 cm. Water acidity pH. The measurement of water pH is carried out using a dedicated probe, a combined glass electrode. This parameter is calibrated based on the curve pattern according to measurements made in buffer solutions of known pH values, 4, 7, 9. Redox, or oxidation reduction measurement is carried out using a dedicated probe, a combined metal electrode. It consists of a platinum indicator half cell with a potential dependent on the oxidizing reducing equilibrium in the solution and a silver chloride reference half cell with a constant potential. The parameter is calibrated based on a measurement made in a standard solution with a known MV value, 220 MV. Specific conductivity, SC, electrical conductivity measurement is a widely used analytical parameter. It is characterized by high reliability, sensitivity, and short response time. A valuable and easy-to-use tool in water quality control is a non-specific summary parameter for all dissolved ionic compounds, salts, acids, bases, and some organic substances in the solution. This technique does not allow for distinguishing individual types of ions. The reading is directly proportional to the combined effect of all ions present in the sample. The measurement is carried out using an integrated circuit that generates a variable voltage applied to metal electrodes. Depending on the electrolyte concentration, as the ion content increases, the resistance decreases, and the current intensity increases, greater conductivity. The higher the conductivity, the higher the conductivity indication, indicating a larger dissolved substance load in the water. Turbidity, transparency, TT. The transparency measurement is carried out using the emission of an infrared light pulse, with a wavelength of approximately 850 nm, in the direction of a detector sensitive to infrared radiation. The suspension in the emission field absorbs the radiation, reducing the amount of light reaching the detector. The more suspension, the proportionally less light received, indicating a higher level of turbidity. Chlorophyll, phytoplankton biomass, CHL. The measurement is carried out using a specially designed probe consisting of an LED emitting diode with a specific wavelength, 450–470 nm, and a detector with a high-pass gel filter of 650 nm. The fluorescent properties of chlorophyll, which emits light of lower energy, red color when exposed to blue light of a specific wavelength, are utilized in the solution. The amount of red light received by the detector is proportional to the amount of chlorophyll in the water. Phycocyanin, a pigment specific to cyanobacteria, PHC. An important parameter in warm periods when the reservoir is used for recreational purposes. An increase in this parameter may indicate an approaching moment of cyanobacterial blooms, an early warning system. The measurement is carried out in a manner analogous to the chlorophyll measurement, using an LED emitting light with a specific wavelength, 620 nm, and a detector, 650 nm. Monitoring water parameters is an essential task for maintaining the health and safety of aquatic ecosystems. Water parameters include physical, chemical and biological factors that affect the quality of water and the organisms that live in it. Some of the most important water parameters are temperature, pH, dissolved oxygen, ammonia, nitrite, nitrate, phosphate, salinity and hardness. These parameters can be measured using various methods and instruments, such as test kits, probes, meters and sensors. Monitoring water parameters regularly can help detect any changes or problems in the water and take appropriate actions to correct them. Planned measurements of BOI sensors, vertical temperature distribution in the water column, TV. Temperature is one of the most important physical factors influencing the rate of reactions occurring in all ecosystems, including aquatic ones. Temperature also affects the value of other parameters, including electrical conductivity. The device automatically compensates the conductivity level to a value of 25 degrees Celsius. The vertical temperature distribution is measured by evenly distributing 5 dedicated semiconductors, digital integrated circuits placed in metal sleeves at levels of 0 cm, -100 cm, 200 cm, -300 cm, and -400 cm. Water acidity pH. The measurement of water pH is carried out using a dedicated probe, a combined glass electrode. This parameter is calibrated based on the curve pattern according to measurements made in buffer solutions of known pH values, 4, 7, 9. Redox, ORP, oxidation reduction measurement is carried out using a dedicated probe, a combined metal electrode. It consists of a platinum indicator half cell with a potential dependent on the oxidizing reducing equilibrium in the solution and a silver chloride reference half cell with a constant potential. The parameter is calibrated based on a measurement made in a standard solution with a known MV value, 220 MV. Specific conductivity, SC, electrical conductivity measurement is a widely used analytical parameter. It is characterized by high reliability, sensitivity, and short response time, a valuable and easy-to-use tool in water quality control as a non-specific summary parameter for all dissolved ionic compounds, salts, acids, bases, and some organic substances, in the solution. This technique does not allow for distinguishing individual types of ions. The reading is directly proportional to the combined effect of all ions present in the sample. The measurement is carried out using an integrated circuit that generates a variable voltage applied to metal electrodes. Depending on the electrolyte concentration, as the ion content increases, the resistance decreases, and the current intensity increases, greater conductivity. The higher the conductivity indication, indicating a larger dissolved substance load in the water, turbidity, transparency, TT. The transparency measurement is carried out using the emission of an infrared light pulse, with a wavelength of approximately 850 nm, in the direction of a detector sensitive to infrared radiation. The suspension in the emission field absorbs the radiation, reducing the amount of light reaching the detector. The more suspension, the proportionally less light received, indicating a higher level of turbidity, chlorophyll, phytoplankton biomass, CHL. The measurement is carried out using a specially designed probe consisting of an LED-emitting diode with a specific wavelength, 450–470 nm, and a detector with a high-pass gel filter of 650 nm. The fluorescent properties of chlorophyll, which emits light of lower energy, red color when exposed to blue light of a specific wavelength, are utilized in the solution. The amount of red light received by the detector is proportional to the amount of chlorophyll in the water. Phycocyanin, a pigment specific to cyanobacteria, PHC, an important parameter in warm periods when the reservoir is used for recreational purposes. An increase in this parameter may indicate an approaching moment of cyanobacterial blooms, an early warning system. The measurement is carried out in a manner analogous to the chlorophyll measurement, using an LED-emitting light with a specific wavelength, 620 nm, and a detector, 650 nm. The solution will implement machine learning mechanisms to minimize the required number of monitoring buoys for effective continuous monitoring and to support decision-making and choosing measurement point locations. Research activities will involve the development of predictive algorithms using random forest, GBM, AdaBoost, XBoost, CatBoost, or other suitable models for training and prediction on large volumes of measurement data from the Internet of Things ecosystem. Therefore, two algorithms, for prediction and classification were chosen. The historical data were obtained in form of the vectors of 10 elements each: location, year, month, temperature TV, pH, redox, AUP, conductivity, SC, turbidity, TT, chlorophyll, CHL, phycocyanin, PHC, and geographical location coordinates, GPS latitude and longitude. It was assumed that the particular data, the parameters values came from sensors listed in the section monitoring water parameters. Finally, historical data was implemented in the form of 240 measurements from 12 parameter sensors. In case of a prediction problem, the random forest algorithm was tested. To implement a random forest model in MATLAB, the built-in function tree bagger can be used. Here is a sample MATLAB code that implements the above algorithm. First, the historical data is loaded and divided into training and testing sets using the partition function with a holdout method of 0.2. Then, the random forest model is trained using the tree bagger function with 100 trees and regression method. The mean squared error and the coefficient of determination, R2, are calculated to evaluate the performance of the model on the testing set. Finally, the model is used to predict the water parameters for new input data. The code can be improved by tuning the hyperparameters of the model or trying other models to achieve better performance. Following is the MATLAB code used to predict the chosen parameters values for particular buoy location, in the particular year and month. The program script, precise MATLAB code, is presented in the manuscript. In case of new, tested data, location 3, year 2023, April, the result of prediction can be seen in the following form. To assess the quality of the obtained model, out-of-bag mean squared error was selected, which is a measure obtained for the random forest model, calculated on the basis of data that was not used to use the tree. This error can range from 0 to infinity. 0 means that the model fits the data perfectly. It is very unlikely in real cases. Higher values mean a larger model prediction error, which means that the model is less accurate and adequate. Out-of-bag mean squared error should be minimized to get the best model. See Figure 5. In this program, code presented in manuscript, the performance of the random forest model is evaluated based on the mean squared error and the coefficient of determination, R², calculated for the testing set. The model can be used to predict the water parameters for other new input data. The decision tree classifier to detect the approaching threat related to cyanobacteria bloom in a lake was introduced. Using historical data from 10 locations in the lake, we extracted relevant parameters, including conductivity, SC, turbidity, TT, chlorophyll, CHL, and the value of a pigment specific to cyanobacteria, PHC. These data were divided into training and testing sets, and the fit tree function in MATLAB was used to train the decision tree classifier. The results of the classifier evaluation showed high classification accuracy and good performance, which was estimated using the F1 score. The F1 score in the random forest classification algorithm measures how well the model classifies objects according to their class label by calculating the harmonic mean of precision and sensitivity for each class. The F1 score can range from 0 to 1, where 1 means a perfect fit of the model to the training data. Additionally, to optimize the classifier parameters, we used the Optimize Hyperparameters option in the fit tree function. Finally, using the classifier, we predicted the value of PHC for new samples and set the threat threshold to 0.2. If the predicted PHC value was higher than the threshold, we identified the cyanobacteria bloom threat. It should be noted that the classifier parameters and thresholds should be adjusted to the specific case and available data. In this work, we used historical data from 10 locations in the lake, but in practice, it may be necessary to supplement the data with additional information, such as weather conditions or the amount of precipitation. The program script, precise MATLAB code, is presented in the manuscript. The program, classifier, MATLAB code in manuscript, used to classify the chosen parameter PHC values for arbitrary chosen data vector, TV equals 6.5, pH equals 7.0, ORP equals 250, SC equals 330, TT equals 11.2, CHL equals 12.4. The trained classifier model, defined for the tested parameter 20 class, returned information on the predicted PHC value in the form, cyanobacterial bloom hazard found. Threshold exceeded 0.2. Minimum objective versus number of function evaluations plot, Figure 6a, is used in optimization proxies to evaluate the performance of an algorithm. It shows how the minimum objective value of the algorithm changes as the number of function evaluations increases. The plot shows how quickly the algorithm is converging towards a minimum objective value as it performs more function evaluations. Ideally, we would like the algorithm to converge quickly, with as few function evaluations as possible. The F1 score, as was said, can range from 0 to 1, where 1 means a perfect fit of the model to the training data. Figure 6b shows that for F1 equals 0.6667 the tree structure is relatively simple. The EnviWise project focuses on developing an innovative early warning platform for monitoring eutrophication in aquatic ecosystems. Continuous monitoring of eutrophication parameters is essential for understanding the complex dynamics of nutrient enrichment, algal growth, and oxygen depletion. Traditional methods involving periodic sampling may not capture rapid changes in water quality. However, the use of advanced measurement probes and remote data transfer technologies enables real-time data collection. This facilitates timely analysis, allowing researchers and environmental managers to detect changes in water quality swiftly and respond accordingly, particularly in addressing acute eutrophication events such as harmful algal blooms. The EnviWise platform aims to improve our understanding of water eutrophication and inform the development of effective management strategies, supporting evidence-based decision-making and integrated approaches to protecting and restoring aquatic ecosystems affected by eutrophication. Machine learning and predictive models play a crucial role in effectively monitoring and forecasting threats in water bodies, such as cyanobacteria blooms. By implementing mechanisms like random forest, GBM, AdaBoost, XBoost, and CatBoost, we can minimize the number of monitoring buoys required for continuous monitoring and support decision-making in selecting measurement point locations. The use of historical data from sensors allows the development of algorithms for classification and prediction, while models such as decision tree classifiers can accurately detect approaching threats. Performance evaluation, optimization of classifier parameters, and the incorporation of additional information, such as weather conditions or precipitation, further enhance the effectiveness of these models. Overall, machine learning and predictive models are invaluable tools in protecting and managing water bodies and their ecosystems. There is currently no similar solution implemented in the Polish market that allows for data aggregation from sensors of various manufacturers and integration of measurements with satellite imagery. The integration of satellite data with local measurements from monitoring buoys and the use of both wired and wireless communication with sensors connected to the measuring station are considered innovative aspects of the project results. The expected outcome of the project is a remote monitoring system for biological and physico-chemical parameters of rivers and reservoirs, which can also find applications in drought prevention and local small retention management projects. The open nature of the solution allows for the adaptation of specific market-available sensors to the requirements of the measurement context. This integrated water quality monitoring system has the potential to significantly contribute to effective water management and situational awareness among stakeholders in the field of water monitoring. Thank you for your attention.